Greetings of the day to everyone. I'm Parvasha Mathur, student of AI and Data Science at IIT Jodhpur. And today I'll walk you through my capstone project titled Understanding Financial Market Dynamics Through Linear Algebra. In this project, I explored how financial stocks affect major Indian banks using matrix analysis and Python programming. So now you can see the problem statement. Financial markets are deeply interconnected. When one institution is hit by a shock, the impact often spreads to others. Using tools from linear algebra, I aim to model and analyze these ripple impacts on four major Indian banks: SBI, ICICI, HDFC, and Axis Bank. Now, this is our matrix A, and this is external shock vector B. I started by defining matrix A, which models how each bank influences itself and its immediate neighbors. Diagonal entries 2 of diagonal entries are set to -1 and all others to 0. Vector B represented external shocks like sudden changes in market conditions. And matrix analysis is done to check symmetry and properties like rank, etc. Firstly, I confirm that matrix A is symmetric because it is equals to its transpose. Now, this is the heat map of matrix A, which shows the interconnection, as you all can see. Now, we are calculating key matrix properties using Python and libraries like NumPy. And here we got the result. Rank is 4, determinant is 4.99, trace is 8, and null space, since A is invertible, null space contains only 0 vector. Here comes our step 3. Solving A into X is equals to B. I solved the metric equation using Python's NumPy library. As you can see the code snippet, this gave me the portfolio adjustments each bank should make in response to external shock. Now, eigenvalue and eigenvector analysis. Next, I analyzed the eigenvalues and eigenvectors of matrix A. The largest eigenvalue was 3.618 and the smallest was 0.381. So largest is dominant. It means it is indicating the most sensitive amplification path, and the smallest is pointing to the weakest link. So this is stable. And now this is the graph. This shows eigenvalues of matrix A. You can see different values here. And this is the heat map for eigenvectors, which we calculated using Python here. And this heat map depicts them. So the x-axis is showing the eigenvector index and the y-axis is showing institution index. Now, Cayley-Hamilton theorem. To further understand the matrix, I verified the Cayley-Hamilton theorem. This theorem says every matrix satisfies its own characteristic polynomial. Okay, so in our case, the matrix A did, confirming its mathematical validity. You can see the calculation here, and hence the theorem is verified. We use the Python also in this. Now comes the portfolio risk assessment. I check the portfolio vector lies in the span of dominant eigenvectors. While the portfolio mainly focuses on SBI and ICIC, you can see here, the dominant vectors support all banks. So the current portfolio doesn't fully align with the most stable configuration, but it can be projected onto that space for improved resilience. So you can see here. Now, using the linear model, I simulated a market shock. The stock prices evolved to SBI 3 units, ICIC 5 units, HDFC 5 units and Axis Bank 3 units. This suggests that ICIC and HDFC would hit the hardest, while SBI and Axis Bank show more resilience. Now, storytelling and the solutions. Finally, I proposed a way to stabilize the system during economic turbulence. By identifying the vulnerable parts of the network through eigenvalues, we can allocate capital or regulation more effectively. Understanding interdependencies allow us to prevent one weak link from causing widespread disruption. So here are few solutions which I have written. Diversity portfolio, monitor the eigenvector spectrum, how we can create the buffers. And to conclude, this project demonstrated how linear algebra and Python can be powerful tools in financial modeling. It helped uncover which banks are most at risk and how the system behaves under stress. Crucial insights for building a more stable financial future. Thank you.